So far, we know how to get the reducible representation for a group of functions or orbitals. Now, we will see how we can extract the irreducible representations that make up the reducible representation. Each reducible representation is comprised of a number of irreducible representations and can be represented as this. Tau is equal to a 1 tau 1 plus a 2 tau 2 plus a 3 tau 3. The coefficient represents the number of the particular irreducible representation that appears in that reducible representation. It can be 0, 1, 2, and whole numbers. 0 signifies that that particular irreducible representation is not present in that particular reducible representation. Or, in layman's terms, not a single set of orbitals or functions transform like that irreducible representation. We can derive the coefficient by using the reduction formula, which states where H is the order of the group, R represents the classes, and R represents the number of operations in a class. Chi-red R is the character of the reducible representation and Chi-ir is the character of the irreducible representation. Now, let's understand how it works. Suppose we have a molecule, let's say a water molecule, which has a fixed molecular symmetry, that is C2V. Since we have a point group, we know the possible symmetry elements associated with it. Here they are E, C2, sigma V, and sigma V prime. From the point group, we can calculate the order and class. Here it is 4 for both. And we are also aware of the possible irreducible representations that the point group contains and their character for each symmetry operation. For C2V, it is a 1A2, B1 and B2. This is what we can get if we know the symmetry of the molecules. Now, our aim is to use these information to define any basis which is associated with the molecules. For example, we can get information on the dipole moment or position of each atom or orbitals, the way they transforms under the symmetry operations of C2V. Suppose we are given a certain basis of water molecule. Now, using the matrix transformation on the basis, we can easily evaluate the reducible representations. Let's say the reducible representation is 9 minus 1, 3, 1. That means the character of E, C2 sigma V, and sigma V prime are 9, minus 1, 3, and 1 respectively. And we know C2V has A1, A2, B1, and B2 irreducible representations. And this is the character table for C2V. Now, we will have to find which irreducible representations are present in this particular reducible representation. We will use the reduction formulae, where we will incorporate the reducible character, the irreducible character of A1, B1, B1, and B2, the order of the group, and number of operation in each class. First, we will check whether A1 is present in that reducible representation or not. For A1, character of E, C2, sigma V, and sigma V prime is 1, 1, 1, and 1 respectively. Here the order H is 4. And number of classes in each operation, NR, is 1. And we are given with the character of the reducible representation for each operation, that is, for E, it is 9, for C2, it is minus 1, for sigma V, it is 3, and for sigma V prime, it is 1. Now, if we put these values in the reduction formulae, we can find out the coefficient for A1, which will be equal to 3. So, total 3 number of A1 present in this reducible representation. Similarly, we can calculate the coefficient for A2, B1 and B2, which are 1, 3 and 2 respectively. So this reducible representation consists of tau is equal to 3A1 plus 1A2 plus 3B1 plus 2B2.